Okay, here we are, 2.5a, College Algebra, and the name of this section is more equation solving. You should find this isn't too painful. Again, it's kind of nice to have all this review or all this. They're trying to make sure that everybody's on the same page, because people that take these college classes most of the time have gone to hundreds of different high schools around the country, and they want to make sure that everybody's on the same page before they get into some new stuff. So they spend the first couple chapters going over basic Algebra 2 material so that you can be sure that all students have had this stuff. So anyway, one of the things that is important to know is how to get rid of stinking fractions. Nobody likes fractions. So what you do is you take the entire thing and multiply it by the least common denominator. Least common denominator is a 6. So we're going to take 6 times this, and 6 times this, and 6 times that. So obviously this one here will stay a 0. And this times this would be 2 times x minus 8, because 6 over 3 is 2. And this will be 6 over 2, which is 3, times x minus 3. And then we get 2x minus 16 plus 3x minus 9 equals 0. And then you just solve it from there. Okay, so not really too terribly difficult. All right, let's look at the caution on page 231. And I was just going to go into this, and now that they say that, I guess I'll just kind of follow the book. The only time you can multiply to get rid of fractions by the least common denominator is when there is an equal sign there. If this were 1/2 x plus 2/3 x, and that's all they gave you, you cannot do that. Okay, that is not the same thing. There has to be an equal sign. If there's an equal sign, then you multiply that 6 times every term on both sides of that equal sign. So very, very important to remember. If you are solving a rational expression, which is like this, without the equal sign, you have to find common denominators and add those. Okay? So, anyway, only with equal signs. Very important to remember that. Now, what the book does, which I'm not really sure why they do that on this one, they multiply the entire thing by the common denominator. But what I suggest doing, which is a lot easier, is notice that our denominators are the same. So if our denominators are the same, our numerators have to be the same. So we can ignore the denominator and just write x squared equals 9. And then we get x equals plus or minus 3. And one of the things that we have to do is look at our answers here. We have 2 answers, and that's because there's a squared there. But notice we have a domain to consider here. 3 does not work in this, because if we use positive 3, we get 0 there and 0 there, which is undefined. So the only number that works is a negative 3. So when I give you something like that, the only answer I want is negative 3. If you give me plus or minus 3, it'll be counted wrong, because that's not the correct answer. So always make sure when you're given fractions or radicals that your radicals are not imaginary and your fractions do not have 0 in the denominator. So something very important there to keep track of when you're doing these. Okay, so just like I said, 2 over 3 equals x over 3, or you could just get rid of the 3's because those are the same. You can do the same when it comes to radicals. If 2 equals 2, then 2 to the n power equals 2 to the n power. Or I guess I should say 2 squared equals 2 to the nth power, then 2 equals n, okay, because the base numbers are the same. But that does not mean that if a to the n equals b to the n, then A equals B. It only works when you're saying if these two are equal, then these two are equal. It doesn't work where these two are equal and these two are different. So for instance, if I have 2 squared equals 2 squared, okay, my exponents are the same, but that does not mean that my bases are the same, okay. It only works if your bases are the same, like I did here, right here. Bases are the same, then the exponents have to be the same, but it doesn't work the other way around. Alright, so let's look at an example. Example number 3 here. It says 5 plus the square root of x plus 7 equals x. Alright, first thing we want to do is we want to isolate the radical. We want to get the radical all by itself on one side of the equal sign. Okay, so we do that. Then we square both sides. When you have a radical, the way to get rid of it is just square both sides. So now I have x plus 7 equals x squared minus 10x plus 25. Now we make that 0. So we have x squared minus 11x plus 18 equals 0, because we brought all that over here. And then we solve from there. And this one, fortunately, we can solve into two binomials, an x minus 9 and an x minus 2, which means x equals 9 or 2. And because we have a radical up here, we need to do some checking to see if this works. Alright, so let's plug 9 in. 5 plus the square root of 9 plus 7 equals 9. So 5 plus square root of 16 is 4 equals 9. That works. Alright, let's try 2. 5 plus square root of 2 plus 7 equals, what was x? 2. So 5 plus the square root of 9 equals 2. 5 plus 3 equals 2. That does not work. So 2 is not a solution. 9 is. So you got to make sure you check these. So middle of page 234, when we raise both sides of an equation to an even power, so like we did on the last one where you squared both sides, the resulting equation can have a solution that the original equation does not, which means that when you plug the answer in, it may not work. It may be an extraneous root. So you've got to do the checking there. Alright, example 4, x minus 3 plus x plus 5 equals 4. Alright, what do I have here? I've got two radicals here. And I said we have to isolate the radical. We need to get a radical on one side of the equal sign by itself. So that's what we're going to do. We're just going to get one radical on the other side so that we just have, let's just move the second one, leave that one there. And that gives me 4 minus the square root of x plus 5. Okay, now I'm going to square both sides. That gives me x minus 3 here, so that's easy. But we have to use FOIL, so I'm going to write it twice just so you can see what's going on here. Okay, 4 times 4 is 16. And outside would be negative 4 square root of x plus 5. So that was this one times that. And now we've got the inside, which is going to be the exact same thing, minus 4 square root of x plus 5. And then we've got last, plus square root of x plus 5, which square root of x plus 5, and they said square it, because you're multiplying this times this. So actually what's going to happen, because we square it, is all of this is going to go away. So that gives me x minus 3 equals 16 minus 8 square root of x plus 5 plus x plus 5. Now we're going to isolate this radical, because we've got to get it by itself. So we've got 16 and 5, which is actually 21. So I'm going to change my 16 to a 21 there. since I added the 5 to it. And then I'm just going to move everything over here except the x plus 5. Alright, so I've got x minus 3 minus 21 minus x equals negative 8 square root of x plus 5. Okay, so that gives me a negative 24 equals negative 8 square root of x plus 5. Divide by negative 8, divide by negative 8, gives me a positive 3 equals the square root of x plus 5. Okay, that's a lot easier. Square both sides, and I get x plus 5, no radical sign, equals 9, or x equals 4. Take 4, plug it back into the original solution, and it works, so that's a good deal. Okay, absolute values can be a little bit more tricky, so let's just look at those real quick. It says in the blue box, top of page 235, the absolute value of x equals a is equivalent to x equals negative a or a. Okay, because the number that's in here just tells you how far away it is from 0 on the number line. So if we had 0 here and we had a number here and a number here, let's say that's 5 and negative 5, the absolute value of negative 5 says how far is it from 0. Absolute value of 5 says how far is it from 0. They're both 5. So see what happens here? The number in here can either be a negative or a positive. Okay, see, negative a or positive a. Alright, if x equals a. Alright, which means, that's some theory there, but the method of doing this just kind of helps you to understand what's going on. The absolute value of x equals 5. Well, what are the possible numbers for x? X can be 5, but it can also be negative 5, right? Because either one of those will give me a 5 for an answer. Alright, that being the case, let's look at one with an equation there. Let's look at x minus 3 equals 2. Alright, so the number in here, x minus 3, whatever that number is, can be equal to 2 or negative 2. So x minus 3 can equal 2, and x minus 3 can equal negative 2. So there's actually two answers here. X equals 5 and x equals 1. So when you're doing these problems, and we'll get into these a little bit more, when you have an absolute value with a variable in it and it's equal to a number, then that absolute value, whatever is in there, the whole thing is going to be equal to, you're going to make two equations, one with a positive number there, which in this case was 2, and one with a negative. So you're going to get two answers so that when you plug them in here, it's a true statement. So let's try that. If x is 5, is that a true statement? Absolute value of 2 is 2? Yes. Alright, let's try 1. Absolute value of 1 minus 3 equals 2. Absolute value of negative 2 is 2. Is that a true statement? Absolute value of negative 2, how far is that from 0? It is 2 away, so yes, it is a true statement. And that's it for lesson 2.5.